Hey everyone, this is post-quantum cryptography. To be entirely honest, this talk will cover a lot more about quantum computing than it will about cryptography. It is a short talk with very esoteric material. Also, it's fairly likely that at least 1 or 2 points I will be hand-waving away the solution because it's either very dense math or because I actually don't know the answer. This is extremely new material for pretty much everyone. But post-quantum cryptography, we need to talk. Why? Whoop. So this is a brief overview of what we're going to be talking about. We're just going to go over a primer on quantum computing, double slit experiment, wave interference, small linear algebra review, Bloch sphere, the Grover's algorithm, and I actually don't have it on here, but I'm also going to talk a little bit about lattice cryptography. So what is quantum computing and why does anyone care? Turns out just about every major powerful force government entity in the world cares a lot. Largely because of this cryptography reason, but also a lot of the other implications of this technology. Basically, it's going to allow us to do math that was previously untenable. The most pressing of those issues is RSA encryption, which is the S in HTTPS when we secure all of our communications over the internet. That RSA encryption is dependent on the assumption that computers have a very hard time finding prime numbers. That is not a challenge for quantum computers. So it poses a very real threat to global security. And as you can see, it's a big issue. But like I say, post-quantum cryptography is kind of like dinosaur repellent. We don't know if it works, and we won't for a while. But you never know. So this is I have a lot of animations in this talk, very few words, because it's kind of hard to communicate a lot of this information. But this is the double slit experiment explained relatively plainly. As the light travels through 2 slits, it comes out the other side, taking on the characteristics of a wave. This is the wave-particle duality of light, and actually pretty much every subatomic particle has this characteristic. You can actually see this in light boxes. You can notice that light escapes out of boxes in cones. If you were to put 2 of those cones right next to each other, they would create a diffraction gradient on the other side. That's where those little sparks are flying over there. And actually, those waves are complementary and subtractive. So the places where the light has common features, the places where these 2 waves take on common characteristics in the same domain space, they cause more light and more intensity on the places where it shows up on the wall. That's why it's sort of flashing over there. And I have another way of expressing this. Here's another animation. So this is the light coming in as a wave. And actually, water will do the same wave pattern. If you put 2 walls here with some slits, it escapes as a wave. And then that is a 2-dimensional representation of the complements of the waves as they collide and interfere. So all of quantum computing is based on the fact that these waves are multi-dimensional objects that we can use for calculation, which is very different from bits. So let's talk about the Bloch circle. The Bloch circle is the mathematical explanation, layman's explanation of what is called a qubit, or quantum bit, qubits. They are, while regular computers compute with bits of 0 and 1, much like this, quantum computers actually compute with everything in between, which is why this is sort of a soft coloring that changes. So this is the Bloch circle. This is a 2-dimensional representation. It actually only refers to describing this kind of computation in real numbers. That's what a Bloch circle indicates, that it's all real numbers. Regular bits are only 0s and 1s, so they just travel this distance over and over. That's all that a regular bit will ever do. They are 1-dimensional pieces of information. However, quantum computers put qubits, which are just particles, into what's called superposition. They sort of straddle that line of the wave-particle duality that I talked about before. And in doing so, they exist as undecided features of reality. I know. So you can actually see an illustration of putting a bit into superposition. And you can notice as this bit is passed through what is called a Hadamard gate, I'll get to that in a moment, it breaks up and it sort of gets soft and fuzzy until it gets measured at the end. This is analogous to the Schrodinger's cat analogy. I'm sure you've heard many times. So this is a dead and alive cat up until it reaches the sensor, at which point, once we look at a particle, the very fabric of reality, the very real rules that define the quantum universe say that mere observation of something defines its characteristics and causes the wave function to collapse into a real figure, like a 1 or a 0, as opposed to all those middle ground things which exist along the rim of this Bloch circle. So now I have to break some news to you. I actually lied. There's no such thing as the Bloch circle. It's called the Bloch sphere. It's actually, so we actually use this kind of notation. It's called Dirac notation or Ket-A notation. And what it does is basically this is a matrix. It's a single dimensional tensor, but it can be actually multi-dimensional. But this matrix is represented by, this is A with respect to the EX domain. So that means those are the terms of the space in which it is defining its calculation. So this is relative to one dimension, this is relative to one dimension, this is relative to one dimension. This describes all three dimensions as they affect a singular entity. And the A, as a result, this is effectively their total feature set. So here's just a real quick visual representation of matrix multiplication, just as a review. I'm not really going to go over it, but it's really helpful for me every time I'm like wondering, looking at a bunch of matrices. It's sort of just the numbers in the second object cascade down the first object after being rotated 90 degrees. And that produces their outcome. This is how general matrix multiplication works. This is sort of the first lesson of linear algebra. So now let's talk about this hypothetical scenario. Weather is incredibly unpredictable and codependent on itself. Cloud cover can increase cloud cover based on densities and stuff. It can increase rain. Sun can increase the rain. Sun can increase the clouds. There's all sorts of different variable factors that go into weather. It's very, very complicated. So this is a hypothetical model of just a Markov state diagram, which we're all pretty familiar with, that just describes how we might transition from a state of cloud cover to rain to sun and the likelihood that they would each cause each other to react. So let's make that a little smaller. Let's move forward. Here's a mathematical representation of that same table. And it's actually showing you the matrix multiplication taking place. But notice that while we can guarantee that there's going to be cloud cover, no rain, and no sun, these are all probabilistic values. They are all determined based on whatever happens. Whatever force is acting on the system will cause some sort of reaction, which results in those probabilities down at the bottom there, at the bottom of the matrix. Not unlike the probabilities that spread across the wall when we shine two separate cones of light on it. So here's a vector representation of that concept. This isn't the same numbers, but these are two matrices being multiplied, and you can see these rounded vectors are being added, and they combine to form where those vectors would be added as you would any other tensors. But it's just sort of a good representation because it has those circles that I've been referencing so much of. So now we come to the Hadamard gate, the first real quantum thing. The Hadamard gate is much analogous to the NOT gate or the OR gate or the AND gate that we use in electrical engineering at the base of all these computers. The Hadamard gate actually puts particles into superposition. In this way, it is analogous to a Fourier transform, simply transforming things into the quantum space where we can perform operations on them prior to transforming them out of the quantum space. You can actually notice this brings in a yes and a no. It flips them, and then it changes the phase of one of the characteristics. And because these two things are out of phase with one another, those operations can actually happen orthogonally. And we can change this particle from being a 100% gonna be a 1 or a 100% gonna be a 0. Instead, we split that into a 1 over root 2 likelihood of being 1 over root 2 likelihood of being a 1 and 1 over root 2 likelihood of being 0. Whatever the probability of it collapsing to either one of those states it was when it was first perpetuated into superposition. I realize I'm talking about a lot of things. It's gonna get a little simpler. So here's the Bloch sphere that I talked about, right? You can see the circle that I described before is actually rotated inside there. But the Bloch sphere is a three-dimensional object because quantum particles are a three-dimensional object. And here is a three-dimensional representation of how we operate on these kinds of bits with quantum gates. So you'll notice that while back, if you remember back to our original animation, we had our bit going from 1 to 0, back to 1, back to 0 on the same dimensional plane. This operates on additional dimensional planes, which is why the arrows split and why they can navigate their way around the circle without touching the sides, which is the key to this. So Grover's algorithm. So I'm not going to talk about the Deutsches Yoga's algorithm, which comes before this, or Shor's algorithm. I'm not going to talk about too much, which is a consequence of this. But this is the first real peek at the power of quantum computing. This is actually a gate diagram, but it's also can be programmatically assigned. And what Grover's algorithm indicates is we can actually traverse an unordered list quadratically faster than classical computers allow us. So imagine we have a very long unordered list, and we're trying to find the number 10 somewhere in that list. Logically, you would assume that in order to check if 10 is in that list, you got to go through at least, on average, half the list. And in worst case scenario, you're going to have to go through the whole list to find this 10. That is just common sense. This is uncommon sense because what's going on here is we are actually traversing that Bloch sphere using extra dimensional space to find our way to our solution without actually having to traverse the entire list. So this is a little bit hard to explain, so I'm going to move forward. But basically, I can totally explain this if you want, but the essential idea here is this is all of our superposition calculations should be treated as a black box because they are by definition a black box, right? If we were to observe them, they would no longer be a black box, and it would actually break the computation. So this is the entire challenge of calculating with a black box, wherein we can only judge so many features about its operations. Generally speaking, we put in a not and a 1 and a 0, because what we're doing is rather than put in a single input into this black box, wait for the output, and judge the characteristics of the box, we're actually breaking the rules a little bit by putting in two inputs that are neither of which wholly decided in what they are. And we run those two computations around separately. And because we have now split the role of collapsing to a single discrete value, because we've split that role into two pieces, we can actually operate with the matrices that define those potentials of 0 and 1. We can use those matrices in their probabilistic form, and we manipulate those, and that's where the secret power of this technology comes from. So I'm going to get a little deeper into Grover's algorithm. So here is a animation of the same process done in indefinitely long period of times. So what's going on here is these are putting bits into superposition. That's what the Hadamard gate does, and then it's flipping them it's rotating them around an axis that is not currently in the basis of the particle that we're measuring. I'll have more pictures. So here's some math. Here's some good math. So this is talking about decoupling, just like splitting our particle. So this is actually the process by which we go through decoupling. I realize that this is like pretty dense and like not so useful, but you'll notice that on either end of this it is multiplying this matrix by a Hadamard matrix, which represents our Hadamard gate. So what is Grover's algorithm actually doing? It's actually what's going on over on this side of the board. So let's say we have this is our unordered list. And all of these are of equal amplitude. The likelihood that our whatever, let's call it a W because that's in here a lot. Our W, the likelihood that our W is in our unordered list is equally likely as every other thing that could be there. However, while in superposition, we can selectively observe certain characteristics depending on the plane that we are observing it in, which is why, if you remember back to my Dirac function, I had an A with respect to the basis of its character. All of linear algebra is based on changing the scope of where we're talking about. So like we're already familiar with this concept because we talk about two-dimensional objects and three-dimensional objects, and we understand that these are fundamentally different. And that in order to describe a three-dimensional object or a three-dimensional location in space, you need a vector with at least 3 numbers associated with it. But because we can split those roles of the unitary matrix, which makes up an existing thing. An existing thing means that the matrix says 0, 0, 1 if it's a three-dimensional matrix, right? It has to sum to 1, and one of those ones has to actually be a 1. So it's a very, very clean-cut thing in normal bit functions and normal reality. But because we can put in things like 1 over the square root of 2 minus I as a probability in those places, when you start multiplying these matrices together, they end up with sort of added constants, minus ones, and that sort of situation. And so if we rotate the basis upon one of our probabilities and not the other, and we selectively observe characteristics about this probability and not the other, then what we can do is we can change the likelihood that that a bit is going to result in 1 or 0. So we can take one of the many probabilities that are going to go into this long list, and we can decide that probability, we're going to intentionally observe it, which means that it's nothing. We collapse it out of the race. It's out of the problem. And because we've collapsed it out of the problem, now we can deal with just the loose ends of the rest of this probabilistic not yet collapsed wave function. And what that means is we can rotate what this other probabilistic particle is addressing. So now they're talking about 2 different areas of space, like hypothetically speaking, but not literally speaking, 2-dimensional object, 3-dimensional object. They're separate. They're existing in separate space. Or rather, this object exists in, the negative world, and this object exists in the positive world. So what we do is when you add non-orthogonal vectors that have partially collapsed wave functions, again, a lot of words, you have a vector that points in a different direction in like multi-dimensional space, and a vector that points in like the normal direction in multi-dimensional space. Those vectors add, it changes the amplitude of that vector in real space. We're gonna have questions at the end. But what that means is that because this amplitude, which we've rotated to be in the negative, because that amplitude is increased, the likelihood of every other part of our unordered list, or the total amplitude of our unordered list goes down. Every other possibility becomes less likely in the face of an amplitude that has been amplified by, basically, we're taking the likelihood that it would be a no, and we're shaving off parts of its characteristics. And because we're taking the no possibility and like dampening it down, we are increasing the yes possibility of this situation, but in like matrix space. So what ends up happening is when you push this amplitude down, all of the likelihood of all the other scenarios goes down because it has to, they go up because it has to maintain a constant amplitude. And if you keep doing this, keep changing the space that you're in, eventually your amplitude will spike so high that you have a clean-cut answer to your problem. So basically, and you'll see a really cool image of this, but basically what's going on here is we're using extra dimensional space to traverse mathematical distance, I guess. So here's actually an oracle, and this is a cool thing. So this is a little bit, basically this describes why we can isolate characteristics of a given state and change them without changing all the other states. We can reduce the likelihood of certain things from happening without actually observing the entire process and ruining it. That operates through this oracle product, which is just a tensor that describes an average function of all the states. So this rotation that we're doing over there from up to down, that's across the mean of all those values. So this is talking about how we break up something into 2 different probabilistic pieces. This is Grover's algorithm expressed as cleanly as I can find it. This is all the states a particular state, traverse over all of them, the likelihood of this equating this, right, as tensor products, this is equal. And because we know this, we can manipulate portions of these tensor products to change things. So this is my favorite animation. This is Grover's algorithm. So you remember our circle from before, where regular bits just do this. And this whole thing is the Bloch circle. This thing is the Bloch sphere. The Bloch sphere uses this extra dimensional space, that I space, those imaginary numbers. They actually are describing a space that has mathematical consequences, even if it's not real space. So what we're doing here is we're cheating. We are cutting across our purple circle by going around. I don't know if this is entirely accurate, but I think that this could be analogous to like particles popping in and out of reality. That's every time they collide with the circle. But over here, this is it doing computation in superposition space. And what we're doing in all these scenarios is basically, because we have that round circle, because we have that round sphere rather than this circle, we are creating a series of hypotenuses that come out of this. And those square roots are predictable. And because they're predictable, that's why we reduce search time quadratically, because it's a square root. It's exactly quadratic, the reduction of time. So that's Grover's algorithm. Here's just a cool, more complicated thing. So basically, all quantum computation right now is about finding ways of moving this arrow across the circle without touching certain walls. And by doing so, we find ourselves to all sorts of cool mathematical realizations that don't really seem possible in a classical world. And we manipulate these by applying various electromagnetic, magnetic, and radiation waves. All right, lattice-based cryptography. So let's get back down to why is this talk necessary in the first place? Because these computers are becoming a thing quite quickly. In fact, you can actually already access the APIs for IBM, Microsoft, and Google's quantum computers. And they're probably giving you a simulation. They're probably running a simulation of a quantum computer on a classical computer, but you can actually access the IBM quantum computers themselves directly. And very soon, these will just be APIs that we can hook into microservices just like everything else. So let's talk about lattice-based cryptography. This is the most promising alternative to RSA encryption that also includes zero-knowledge proofs, which is necessary for public key cryptography. So on a lattice, let's say it's a two-dimensional lattice. We want to hide information. We can simply not describe the entire lattice, but instead just describe the base, right? Just like the one-dimension, two-dimension, three-dimension thing I was talking about before, all we need to describe is the minimal number of characteristics to describe a coordinate on this plane. That is like part of our public key, essentially. What is our private key is a destination on the plane. Now, in what are called short lattices, which is something that looks a little bit more like this is very easy, right? The shortest lattice of all is just a perfect grid. What are the coordinates on a grid? Exactly where the coordinates are. But if I were to ask you to find me a point, find me the closest coordinate to this point without it actually being that point, the problem gets increasingly difficult the longer and wider we make our lattice. Because you'll start to notice the relative amount of, I guess, like length to width going on here keeps changing. So the amount that you should traverse, say, vertically versus horizontally keeps changing based on the length that you provide. So by submitting different kinds of bases, we can create all sorts of different types of cryptographic keys. And what's also cool is this is a two-dimensional lattice. But what if this was a 100,000th dimensional lattice? Then it starts to become literally beyond the scope of even the seemingly infinite calculations that we've unlocked with these new superpositions. So this is what I would assert is like a good move forward. It's also where most of the innovation is going on. We're also going to talk about two other quantum-resistant cryptography mechanisms. So we have Lamport signatures, which I think are generally more popular in the blockchain space, which is they require you to limit your the amount of messages you can send. Every time you use a key, you can only use it once, which is a real pain. So you can use like trees and stuff to make keys a little bit more reusable, but that is a pretty major stipulation. And then Microsoft's Picnic, which was the original premise of this talk, uh, is really just very similar to RSA actually, but uses more modulation. It uses extra degrees of modulation, and also uses a random bit flip in the middle. And basically, the idea here is that there's a because of this binary randomness, you can add it only like in one place, and it still increases the complexity of the modularization by like potentially indefinitely, simply because that's how like modulo works. So here's another cool animation. This is an animation of decoherence, which I showed you guys before. But basically, this shows that any particles that we don't measure right away, they can't stay in superposition. It's very, very fragile. And this is one of the big challenges of quantum computing today. It's very, very fragile to keep something in a state. So they have this problem called decoherence, which is why if you're reading about quantum computers going forward, they'll tell you that they have so many entangled bits or so many annealed bits or so many of this, that, and the other thing, but none of those statistics really matter unless they talk about decoherence and how big of a problem it is. Because every single one of these problems that we're solving, all those things with the big sphere, none of those, or very few of those rather, end up with a absolute discrete solution. Usually they just end up with a probability that approaches one, which is true about all quantum computation going forward for the most part. We're sort of banking on the likelihood of things rather than knowing them with absolute certainty. So this is wacky. I wanted to show you guys this because this is a guy's attempt to visualize the singularly entangled Grover's algorithm. This is that same diagram I showed you before with the with all the logic gates. This is that same thing expressed in like sort of animations, and you can tell these are iterations. By the way, that first one is they're all the same thing, but the first one is his first attempt, and you'll notice he keeps getting more complex because he keeps finding out that he can't express enough information with his limited fields of vision. There's just only so many dimensions of complexity you can possibly express visually, and he kind of hits his limit here. And we're gonna kind of keep hitting this limit. So there is like, at a certain point, this technology is just math, and you have to like be able to pivot from one like planar basis to the other, and just sort of be okay with that without needing any sort of natural intuition around it, because there really isn't any for quantum physics. Yeah, so that's my talk. I'm happy to answer any questions if anyone is looking for some. I'm sure that was really dense. If you want me to go back to a slide, that could probably be really helpful. Yeah, go ahead.
So I was wondering, you mentioned in the beginning how quantum computers can solve the whole prime number thing very quickly. Can you give us some kind of scale? Because I know regular linear computers or binary computers can do it very slowly.
Absolutely. So Shor's algorithm, which is the algorithm to do that, which is an extrapolation, it's a generalization of Grover's algorithm, which I showed you guys explicitly because it sort of exists in that middle. And if you delve into quantum computing, those three algorithms I mentioned, you have to go through them. They're sort of prerequisites to understanding anything in this space. But Shor's algorithm is an exponential speedup in prime number factorization. And you'll actually notice something really interesting about this. Because we are now using imaginary numbers in our calculations, we create things that are fundamentally unfactorable, which is really interesting, and like which is why we're colliding with a lot more of these unsolvable problems due to quantum computing, because we just learned that some things are fundamentally unfactorable. Just like, finding the square root of I is a lot like defining the object in superposition. It doesn't really exist. It exists mathematically represented, but it's not actually a real representation of what's going on in reality. Does that answer your question? Excellent. Anyone else? There's a lot of stuff in here. If you want to look at any of these animations or ask me what they mean, I'm happy to do that. We can go back to go back to this guy. Yeah, this is really powerful just because. So what's essentially going on here, and the way that we split this, the way that this concept is originally introduced, is a man comes to your house with a black box. He says, "Tell me what kind of function is in this black box." And conventional way of thinking would, and you're not just trying to figure out what the function is. All you're actually trying to figure out is if it's balanced or mixed, which is to say, is this a reversible function by which it's equally likely that any outcome will happen, or is it mixed, in which case it's oriented towards something and it's actually going to change the outcome based on our input. And again, conventional thinking would say, all right, you put something through, you see what comes out the other end, you have like some idea of what the box does, and you do it again, and then you have a better idea of what the box does. It probably takes at least, at least 2 iterations to like have any sort of say about what this box does. But that's not actually true, because we're not actually, in reality, we're not actually limited to only putting one input. We can put multiple inputs. They just have to be probabilistic values and not actualized tensors. So that's really the cheat code here, is we're figuring out that places where it seems that there is one input, it's actually, we can input an entire matrix. And obviously that unlocks quite a few cool computational things. No questions? Yeah, go ahead.
So, is this on? Um, Getting the impression that current means of encryption and security are endangered from this technology, and what kind of timeline are we looking at before we're all in trouble?
That's a great question. So there's this term you'll see floating around a lot called quantum supremacy, which is the threshold by which quantum computers are now solving problems that are simply out of range of classical computers. We are arguably already there. It depends on who you ask. Another big part of this is it's a little hard to discern how far along the technology's come, because most of this technology is being developed in secret, because the stakes are high. This is, insofar as I'm concerned, the Manhattan Project of cybersecurity. I'm sorry, can you repeat your question?
How much trouble are we in?
Right. So it's like hard to say, because a lot of people are also a lot of smoke and mirrors. IBM announced their first commercial quantum computer at the CES, but that's very different from what we would call a universal quantum computer, which is something that can do more or less whatever a computer can do, plus the quantum stuff. Quantum computers are much more analogous to GPUs than they are to CPUs. They don't make lots of quick, small calculations. That's not really what they're for. They're really for large-scale, repetitive, multivariable problems. So it's unlikely that a quantum computer will ever replace your laptop. That doesn't really make sense. You might only borrow it for certain circumstances that require like super multivariable problems. But yeah, they certainly are emerging. I've been paying attention to this field for like maybe like 4 or 5 years. I actually was doing a little bit of quantum mechanics back when I was doing research on supercapacitors, which are sort of like electricity sponges. So I was doing work on that for a while, so I started to get interested in it, but it's pretty undeniable that the pace of advancement has picked up dramatically. There's pretty much a new article every day now, and new papers every week. That was not the case 5 years ago. It's become a stressor for governments. Actually, our government just passed a bipartisan bill, not just a little while ago, but our government actually just passed a bipartisan bill for $1.2 billion in funding for quantum computing progress in the U.S. and China's already invested something like 10 billion. So this is certainly a big direction for both like our government as well as others. And as you can see, it's really only big players right now. I think like the minimum investment on quantum computers is like $25 million, but that doesn't mean we can't use their APIs. Yeah, go ahead. what a query would look like. I would say that what you're gonna have to do when you use those APIs is you kind of have to have an understanding of both the gate logic as well as the programming logic. I'm sure that there's like a convertible thing between the two. Uh, what would that language look like? I mean, it looks mostly like matrix multiplication, I guess. Sure. So like one of our biggest challenges in modern computing is simulating molecules. Simulating complex molecules is incredibly difficult because their complexity increases factorially with each added subatomic particle. So if you have like a regular atom with like one electron, right, hydrogen atom with one electron floating around, very simple, very easy to understand. But as soon as you add another molecule, both like the electron, the core of the hydrogen, as well as whatever your new atom is, all of those have relationships with each other. There's no two that don't have a relationship with each other. So we really can't simulate complex molecules at all in modern era. This type of technology will allow us to simulate enormously complex molecules. Again, with it'll just sort of look like huge matrices with like some imaginary numbers thrown in every once in a while. But that is really one of the major things that this will unlock is molecular design and genetic engineering and machine learning is also a huge, very, very big part of this technology. It goes very, very hand in hand, as you can imagine, because in most machine learning models, we have to train it, and that's so many iterations through a system just on repeat. This is creating probabilistic scenarios that are running basically a million times and just telling you what the likelihood of every outcome is. That's just sounds like a machine learning speedup to me. Does that answer your question? Go ahead.
Regarding the politics of this, why governments are pushing this, do you think they're doing it more for like protein folding, gene sequencing, SETI, or the too many secrets thing?
Too many secrets is definitely probably the leading cause. I mean, like the militaristic component really like drives the urgency, doesn't it? But outside of that, I mean, I kind of just think in the developed world, if you're not developing on quantum computers and you're not moving that technology forward, you're like getting left behind right now, because this is a technology, while not universal in its applications, extremely broad in its applications, and like certainly the forefront of a lot of innovation that's about to show up. Does that answer your question?
I guess I was just wondering where are governments putting more of their money in, which of those kinds of I guess means to an ends kind of thing.
Well, the post-quantum cryptography thing, I think people have settled down a little bit more about, just because we've had more people look at the issue and building out more solutions to that problem. Outside of that, I imagine, I mean, also just for general purpose, like super multivariable problems, like economics is like an incredibly multivariable problem with like infinite dependencies. That's precisely like an area where like a government might be more interested. But governments, I mean, like everyone's sort of guessing right now in this field. Like we know some things and we don't know others. For example, one of the really cool things that just happened recently, a company that nobody had heard of called IonQ in Maryland now has the most entangled bits of any quantum computer with the least amount of decoherence, which is incredibly impressive. And it's super different because while most of these other things are using electrons as their qubits, you can really use any subatomic particle you want. Most are using electrons or photons. Photons actually make really bad qubits, but this company IonQ are actually using the quantum properties of atoms themselves, because actually all this wave particle duality that I talked about actually goes all the way up. It applies to every single particle in the entire universe because E equals mc squared. So yeah, we are actually wave functions ourselves, just really complicated ones. Yeah, I think that answered your question. Anything else? Anybody want to see any cool animations again?
So I see a processor pipeline here, right? Like I see my 3-stage, 7-stage, whatever, blah, 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 opinion that you want to talk about. what do you have in terms of like a storage element, right? Like a traditional computer has a bank of RAM in which I can store information and then act on it later. What is does a quantum computer have the equivalent of, or does it even need it?
Right. So quantum computers can actually perform every gate operation that we do in a classical computer. It's a little silly use of the technology. Um, in fact, none of this technology has any advantage on classical computers until this Hadamard gate shows up. So you're asking about memory. We certainly aren't recording things in superposition because there is literally no way of doing that. So any information that gets recorded is coming out the other side, which means it's a collapsed wave function, which means that it's just ones or zeros, which means that we store it just like everything else.
What are some of the energy implications of this? So you're talking about you have to create these quantum particles. So it seems like creating those might be expensive if you can't use a photon, I guess.
I don't know the energy costs. It's probably a lot. They're generally very big machines, and usually they have to operate just around absolute zero, which is part of the reason that this is so difficult. Most of this technology is built on our modern understanding of superconductors, which is like frustratingly not as much as we would want it to be. So we just sort of have to live by the rules of supercapacitors as we know them, which is very, very, very cold. That's the only way that any of these things work. So yeah, it's like definitely a huge energy undertaking.